All right, here we go. So this is the second one. So this would be 163, I think. Yeah, 163. So let's go over one of these thoroughly. So we've got cable AB attached to strut BC. Find the tension and shear in the strut that are caused by the cable. Okay? So when you're given these sheets, you just fill in the sheets. You don't need to put anything extra on there. Just put your solution on there, fill in the answer blanks, and turn them in. Okay, so that's how that's set up. All right, so what we got to do here, the first thing to do is to find the force that goes from B to A. And, you know, this is something I've mentioned. I'll mention it again. You should know how to do this now, okay? This is a skill that you need. The way you do this is you get the position vector from B to A. To do that, you take RA minus RB. Okay, remember to reverse the order on the letters when you do the subtraction. So RA is 3 minus 4, 7. RB is negative 1, 2, 2. Subtract, you get 4 minus 6, 5. Take the square root of sum of the squares, and you get 8.775. Divide that through the position vector, you'll get a unit vector from B to A. Factor that up by the magnitude of the force, 800, and you'll get the force vector, 365 minus 547 and 456. Okay, so you find the position vector from B to A. You essentially take the length out of that line because you want a unit vector. So you remove the length as a magnitude, and then you put in the force magnitude. So one way to think about that process is you're replacing the length magnitude with the force magnitude on the vector. That's one way to be thinking about that, okay? So we okay with that. We get the force vector. And again, I've said it 10 times already. I'll say it 11. Just be able to do that without hints or prompts or anything. Practice a couple. Be sure you can walk through that, okay?
So
yes?
The force vector that we'll be finding, would that be the shear force?
We're going to find both, in this case, the axial force, which is the tension, and the shear. This is just the force that goes from B to A.
Yeah.
Some random force at some random angle. We're going to do a dot product and get the tension, and then we'll do some vector stuff and get the shear.
Okay.
So we're going to do both. Okay. All right, so we got that initial vector. Good to go. Okay. All right, now we want to find UCB. All right. Now I want a unit vector. Now I'm noticing that if I kind of take the component of that force that goes in the direction of that line, it's going to kind of do something like that, it looks like, doesn't it? So that's why I'm going C to B, because that's in the same direction as that component of force. Okay? So I'm going to use UCB. So I'm going to take RB minus RC, get RCB, take the square root of sum of the squares, I get 7.071. Divide through by that, I get the unit vector from C to B. Okay. So any questions on that? Doing all right? Okay. So what I've got now is the force that goes from B to A and the unit vector from C to B. So if I want to find the axial force in that strut there, I'm going to dot them together. Okay. So when I get a dot product, what I get is I get the magnitude of the force times the magnitude of the unit vector, which is just 1, so that's just the magnitude of force, and then I also include the cosine of theta. All that is done when I do a dot product. So I'll take the magnitude of the force, 800, times the magnitude of the unit vector, which is 1, times the cosine of the angle in between, and that'll get me the projection of that 800 Newton force onto that strut. That's what that'll get me. It just magically comes out if I do a dot product, okay? So I've got the force vector and the unit vector, and I dot them, is what I do. So I got those two vectors, I dot them together, and then I add up the three components there, or not components, that's not the right word, I shouldn't use that word. I add up the three products. Okay, Okay, so I take the like components and multiply them together. So fx with ux, fy with uy, fc with uz, multiply them together, add up the products, carry my signs along, and I'll get 374. Okay. So what that means is that internal force in the strut is directed from C to B. So that's going to pull. That's a tension is what that is. Okay. So that's 374 newtons. Okay. Now I know the total force is 800. I know this tension is 374, so I can use the theorem of Pythagoras to get the shear. If all I want is the magnitude of the shear, I can just use theorem of Pythagoras and back into what it is, okay? Because what I've got here is I've got the tension is like that. The shear will be like that, and that vector, that original tension in the cable is the original vector, the force vector, okay? And I've got a component relationship thing going on there, okay? Like that. So I can use the theorem of Pythagoras and back into what the shear would be. It would be the total squared minus the tension squared, and then take a square root. Okay, I'm kind of working back through the theorem of Pythagoras to get that, and that's 707. So if I apply that force to that strut, I've got a tension in the strut of 374, and I've got a shear of 707. And once I've got that, we can use the stuff that we'll take in the spring for most of you, and that will allow us to design that thing so it can handle those forces. Okay. Okay, so we okay with that? Right. Now there's other ways to do this too. Now you can do it vector style if you want also. To do it vector style, you would get the tension vector. You'd take the magnitude that we got for the tension, the 374, and multiply it through the unit vector from C to B, and that would get you a tension vector right there. Then you could find the shear vector knowing that it's a component of FBA. So you take FBA, the total vector, take away the tension vector, and you get the shear vector. And then you could take the square root of sum of the squares and get the F shear, if you like. So you could do it either way. If all you need is a magnitude, the theorem of Pythagoras method is quicker and easier. But if you need vectors, this is how you would proceed with that.
Is that just like finding the normal vector then?
What's that now?
Finding a shear is just like finding the normal vector between your new vector of the force times your unit vector.
What do you mean by normal vector?
It's like perpendicular.
Yeah, it's perpendicular. Now,
Perpendicular.
are you thinking cross products or something, or
Kind of, I guess.
Yeah, I'm not sure if, I don't think those pop out, so that's why I'm a question about what you exactly mean by normal vector. But this is normal, right? But I'm finding it by vector subtraction, and I don't think a cross won't just knock this out.
No, it's like the projection is what I'm thinking.
Yeah, it is, right? Yeah.
Projection vector, and then you just find the normal between the projection and your u.
Yeah, essentially.
So which one is much easier to find, like this one or the other?
The other one's easier if all you need is a magnitude. See, the other one, all it does, it gets you directly to the magnitude by using theorem of Pythagoras. If you want a vector, you've got to go through the other steps to get there. So it just depends what you're being asked to do. Okay? If they just say what's the magnitude of the shear, I would just do it that way because it's quicker, simpler. Okay.
Are you ever going to ask us for the vector, the shear vector?
I could. Okay, I mean,
Would it be useful? I guess all you would care about is the force, right?
I don't know. I mean,
in this class, would we?
I'm always very reluctant to answer general questions like that. You know, it's you just never know. I've used stuff working. You just never know what you got to pull out of the hat to solve something. So, you know, I can't just give you a nice clean example of here's where you'd use it, but you know, it could come up. And I guess to kind of, you know, I know people get concerned about tests. Just to kind of mention this, normally the way I try and structure the tests is about 70% of them is just basic information. You know, can you do a dot? Can you do a cross? Can you do, you know, we'll do crosses later. You know, can you do this and that? Okay, another 20% is a little bit more higher level information. And the last 10% is kind of open-ended, okay? Now those numbers I didn't pull out of a hat because what is 70% grade-wise? That's a C, isn't it? Okay, so if you can do the basic information, you get a C. If you can do a little bit more advanced stuff, you'll get a B. If you can do a little harder stuff and more creatively, you can get an A. That's kind of how I structure the test. So a question like you ask, you know, I would never say never, but I would say that I wouldn't put something like that on a test and make it worth 40%. You know, I would not do that. But the more advanced stuff, I could put anything on the test. But watch the points on the test because, you know, they're very indicative, of course, what they're worth and how much time you want to spend on them. Okay, so you might see some harder stuff that's only worth 5 points, and that's kind of what I'm doing with that. It might take you a while to do it, but you should do the other stuff first, you know. Okay, so that just kind of expand on that a little bit. Okay. Other questions on that? Okay. So that's kind of the process on that. You know, you can use this exact same process on the previous problem. It's the same deal, you know. There are the answers there. You know, I'll get you some intermediate check answers there. And, okay, so you can follow that same process through. I think this 163, all I asked for was the magnitude of the shear, but I went and showed you the vector stuff because I asked for the vector stuff on 162, so that'll be a template of how to do it, okay. Okay, then we got a couple equilibrium problems. So on this one, 171, I'll maybe run through this and kind of give you some hints on the one following. So are there any questions on any of this stuff here so far? Okay. So 171 here, what we want is we want a free body diagram that involves all those cable forces, because that's what you want to find are the magnitudes of the cable forces to keep the ring in equilibrium. So there's my free body diagram, and whenever I cut through something, it becomes a force, because that's what's called a contact force. Those are all cables, so they all pull, is what they all do. So that gets me down to this free body diagram here. Now I went ahead and did the trigonometry on the dimensions to get the angles, so I got an arctan of 1.5 over 3, and that's 26.6, and an arctan of 4 over 3 is 53.13. So that's how I generated that free body diagram with the angles. Okay. So do we got questions on that? Right. Yeah, on this one the ring has no mass. Right, that's a good point. You know, there was no mention of it, and you know, knowing that rings are often kind of small, you can kind of get to that. But sometimes that is kind of an assumption you got to make by omission, if you know what I mean. Being as there's no mention of it, I would make that assumption. Yeah. Okay. All right. And you know, keep in mind when you start working, in school you lose sleep over solving the problem. In work you lose sleep over the assumptions you make, because the book always says, you know, assume this and assume that. But when you start working, you got to be the one who figures out what you're going to assume, and that's when you start kind of going, I don't know, you know, can I do this? And you know, and that's where safety factors come in, right? You know, because we don't want stuff to break. So, and you know, a safety factor is really the reflection of how confident you are about your analysis and how confident you are and how well the materials are built and are put together and all that. You know. Okay, now I'm going to start with sum of Fy, okay, because I know I'm heading into 2 equations and 2 unknowns, And if I use sum of Fy, I'll relate AB directly to AC, and I will not have to concern myself with the 860. So I'll get a nice simple equation there. Now keep in mind on a test, you don't have a programmable calculator, you've got a simple calculator, so you do have to work through this. However, on homework, you can use whatever tool you want. I don't care, and I would encourage you to learn how to use the different tools you've got at your disposal, your TI or a spreadsheet or whatever the heck works for you, use it, okay? When I'm working, I've got a TI, not a TI, I've got an HP 15C, and I can program that thing, and I can do a lot with that. And if that doesn't work, I can use a spreadsheet. Those are the things I use when I'm working. Whatever works for you, use. Okay, so we're going to go sum of Fy first because we've got two equations to choose from, right? Sum of Fx is 0 because this is 2D equilibrium, and sum of Fy is 0. That's our two choices we've got. So we've got to figure out which one to use. So start with the simpler one first, which is sum of Fy is 0. All right. And then it's just a little trigonometry exercise then. What we're doing for the y components is we're using the sine function that's opposite the angle. So that's FAB y up and FAC y down. All right. So sum of Fy is 0, sine 26.6 FAB minus sine 53.13 FAC. Notice it's sine 26.6 FAB. It is not sine 26.6 FABY. I see people doing that sometimes. That's not correct. And it does matter because I'm trying to get back to what FAB and FAC are. So if I take sine of 26.6 times the actual full magnitude of AB, that gets me the y component that I want to put into this equation. That way I can back out and solve for what FAB is. Same thing with FAC. So the trig components get you the x and y, components that you want, and then the full magnitude of the force goes into the equation also. Okay. And what I'm going to do is work that algebraically down so I can get a substitution going. So I got FAB is 1.79 FAC when I work through that. Okay. And notice, and step by step, right? I overkill that a little bit because that cuts down on my errors, all right? And just start to develop your own approaches, but when you start skipping steps, you start dropping signs and doing all that stuff that gets us into trouble. So take a little extra time walking through. It saves you in the long run having to go back and fix things. Because when you work through something once, it's nice and clean and simple. When you start going back and correcting errors, it starts getting complicated all of a sudden. And that's double for when you start designing stuff. I spent a week once designing a road intersection the size of this room. Real complicated calculations, like going from a valley gutter to a crown gutter and changing widths and all this crazy stuff. And I had coordinates all over the place. And, that took hours. And then Friday, the guy leans over my shoulder and tells me I was using the wrong base map because they had two base maps. So I was unhappy about that. But point is, if you make that little mistake on Monday, man, it's going to get to Friday and you've got that mistake that's worked its way through. Boy, that's a bad feeling. Okay, it doesn't feel good. Okay, all right, there we go. So now we've done some of Fy, and we've got to the fact that FAB is 1.79 FBC. And I've got a typo there. Is that AC that it is? 1.79 FAC. Yeah, I think it is. Let's go back and look. Yeah, it is. This should be AC right here. Okay. Here we go. So now I've got a nice clean substitution. Now I can go with sum of Fx is 0. So sum of Fx is 0. It's negative cosine 26.6 FAB. That's to the left, so that's a negative. The cosine function gets me the x component of FAB. It gets me that one. That's the side adjacent to the angle. And then I've got cosine 53.13 times FAC right there. They're both negative because they both go to the left. And then plus 860. Okay. Then I work through that and I get 0.894 FAB plus 0.6 FAC is 860. And I take that number and I substitute it in like that. That gets me the equation in terms of FBC. work through that. I get 2.2 FBC is 860. FBC is 391. I can take that and pop it back. No, I can't. Yeah, I can. Man, darn it. I keep getting that BC stuff creeping in there, don't I? Darn it, I'm sorry about that. AC, AC, AC.
1.60 BC.
Oh, man. Okay, that should be, yikes. This is a problem, isn't it? Okay, so the 1.60, where did that come from? That's the 0.894 times, okay, so this should be AC. There we go, and that should be 0.6 is, all right, this is all AC, right? There we go. Okay, there we go. Yeah, okay, that's all good now. All right. Okay. All right, so then I did a substitution there. I got FAB is 1.79 FAC. I plug it in here. That gets the equation entirely in terms of FAC. So 2.2 FAC is 860, so FAC is 391. Substitute that back in the top relationship, and I'll get FAB at 699. Okay. Now, on that homework, I handed it back. A number of people had slightly different answers than me on account of rounding, but that didn't cause any trouble because everyone showed their work and I could follow it through. So if you get something a little different than this, my general rule is you should be within 1% of the answers you're given. If you're carrying 3 sig figs and you're showing your work, that's just fine. That's no problem. Okay. It's probably just differences in rounding. Okay, now let's have a look at the one after this one. All right, now on this one, A and F are not at the same height. So that is, you can't assume that from this, okay? Can't do that. That's for part 2, is really when that enters in. So this is an awful lot like the one we did before. I think you're going to want to get this into newtons, right? Because you don't do statics with mass, you do it with weight. And then you're just going to take that around the pulley and put it right there, right? However many newtons that is. And get you a nice free body diagram of the ring. So that would be very similar to what we just did. And then the other thing I'd like off of this is part 2 there, find the angle DF mixed with the horizontal. So I'd like to know, what is this angle right here? Call it theta DF. That's just a pulley that's on a cable. And there's multiple ways to solve that. I'll let you figure that out, but there's more than one way to do it. So somehow just get me that angle that cable makes with the horizontal. We got any questions on that? All right. You good?
DF, does that say?
What's that now?
Is there something on this cable DF for how about 4 meters?
Yeah, that may or may not help you though. I don't think it will help you too much, honestly.
Oh, okay.
Okay. All right. So you just want that angle in there. That stuff's due Monday. Call it good here.